In this video, we'll be looking at how to parse through a fairly complicated setup. That's the setup that creates the tentacles. I'll pretend I've never seen the setup before and try to explain some of my thought process as I go through and try to understand it. We'll also be looking at how we can try to come up with a plan for how to create OTLs out of our setup while we're parsing through it. It is important that we understand the setup because we'll also always be on the lookout for ways to improve it. Often people make setups under deadline pressure and don't make them procedural enough to be turned into OTLs, or even sometimes they make mistakes. And it's a good idea to be on the lookout for rough edges we can polish off. Alright, so let's have a look at our tentacles setup. So I'm going to dive inside here. And this looks pretty complicated, and it may be a little bit daunting to read all of this. But if we go step by step, it actually isn't too bad, and we'll see that as we go. And we'll look at some techniques we can use to try to understand fairly complicated setups like this. Now, the first thing that we're going to be doing is looking for inputs. If you remember, we said that OTLs need to be as shot and hip file independent as possible. In other words, we want to make them as procedural as possible. And that means that it's extremely important to know what the inputs to our setup are. So the way that we're going to find inputs is we're going to generally hope that they are kind of towards the top of the setup. But that's not always the case, and some people are kind of badly organized about these things and put object merges that grab things out from outside the setup in places that are like halfway down. So what we're really going to be looking for is object merges especially, and nodes that don't themselves have inputs as another way of looking for things. So we can see a few of them here. You can look at this one. This looks like it's just some modeled shape. We don't really care what it is for now. We're just trying to figure out where the inputs of the setup are. So we're going to say this is probably not an input to the setup, but it might be. So let's just kind of move this off to the side and make a mental note of it. Down here we see a circle, and if we just follow it a little bit, it looks like it's just, let's zoom in on it and step through it. It looks like it's just modeling another shape. This looks like something that may be simple enough to just promote and not be an input to the setup, so we'll just kind of leave it. Up here, we finally have a couple of object merges, and it looks like these are referencing things from outside the setup. So here we have found our first set of inputs. So rather than just making a mental note of these, since we know that for sure they're inputs, let's just move them all the way up to the top. And we're even going to color them something like blue, just so that they're easy to find again. In fact, let's make them a brighter color of blue so that they're easy to see. And over here we have a line, and this is just, it's just a line. It's probably easy enough to just promote some parameters here, so we're going to say this isn't an input. And over here we have our grid. And if we look at just kind of at a glance what's happening here, we can see that we have a grid. We are doing some copy based on something that happens to that grid, and we're copying lines. And if we even look at the copy, we can see that we have copied a bunch of lines. So we're going to just kind of guess that this is where the setup sort of starts, is with this grid, and that this is the emission surface for our tentacles. And since we have already gone through and made a handy emitter OTL, that means that we can say, yes, this is an input to the system, and we've actually identified a way in which we can make the system better. We can use our emitter OTL, or at least provide some input instead of using this non-procedural grid that someone just created. So we're going to say this is an input to the system. Now you might be wondering, why aren't we just immediately replacing this grid with an object merge that references one of the emitter OTLs? And the reason for that is that I want to go through and try as best as I can to understand how the setup works before I start tinkering with it. Usually it's a good idea not to break things that we don't understand as much as we can. What we might do is just add a sticky note here and just say something like to do look into replacing this grid with a, let's say, an OTL input. And that way we can remember that we have something to do here. All right, so let's start stepping through this setup. And since we've kind of identified where the setup starts with this grid that represents our emission surface, let's just start there and start stepping through it. So the first thing that we're going to hit is a scatter SOP, and we can see that both from the way that the node is named and the fact that there's this copy SOP down here, that this is probably controlling how many tentacles we're going to have in the end. So it's, I think, fairly straightforward to conclude that we will probably want to promote some parameter off of this node. Let's say the force total count parameter, so that we can get 150 tentacles, and we can change that number. So we're going to establish some convention for when we come back later and start making OTLs to identify which nodes need parameters promoted. In this case, I'm just going to go ahead and color it green so it's easy to find again. Our next node is a wrangle node, and it looks like it's just creating some attributes. It's affecting the normals, it's affecting the p-scale, and then it's adding some attributes that we may not know what they're for yet. Now, notice that whoever made this setup has added some spare parameters to this wrangle, which means that when the person was creating the setup, or maybe while they were using it in their shot, they realized that they needed to control something in the Vex code for this node. This is a good clue to us that we might need to be able to control this from the OTL's interface as well. So let's just go ahead and mark it green. And in this case, we can see that because it's affecting the normal, we can just look at the normal, and we know it's going into a copy. We can kind of deduce that this direction parameter is the direction that the tentacles will be pointing, which means that indeed this will be a very important thing to promote. Next, it looks like we're just multiplying some noise against the p-scale attribute, which also seems like an important thing to be able to control. So let's just color that node green also, and move on. Now that we've hit a copy, let's just make sure that we understand what's being copied. And the only thing that's kind of weird here is that we have a wrangle that's creating some attributes that we don't necessarily know what they're for yet. But it looks like we have an attribute that fades off along the line, so it'll be 0 at the base of the line and 1 at the tip of the line. So that seems like something that'll be generally quite useful. And then we have another one that just has the point numbers before it gets copied. So if we want to understand how this works, or maybe we just don't know what this does, we might just say something like at CD equals at line offset, for example. And we can see very visually, this is what that attribute is doing. And then maybe just get rid of it so that we don't change the setup while we are trying to understand it still. Okay, moving on. Now we have another node where the setup creator has promoted a bunch of spare parameters. So I'm going to just almost automatically mark it green because of that. And we can also see that we're doing a bunch of things with noise. We don't necessarily have to go through and try to understand every line of the Vex code. We can just see, oh, we're doing some kind of noise function. We're going to apply a ramp to it, and we're just going to add it to our point position. And we can see from having displayed the node that we are adding some kind of noisy motion to the lines. Now, note that in a lot of these wrangles, I have gone through and added fairly detailed comments so that if you want to, you can go back and try to understand some of the details behind this setup. But we're not going to be going into too much detail as to how the Vex code works in the videos themselves, because we want to focus as much as possible on how to get to a point where we're ready to make OTLs as quickly as possible. All right, so moving on, we have something that the setup author has called flow normals. So since we can see that it's modifying our normals in some way, we might just turn on normal display to see what it did. And if we look at the node before it, we can see that before it, the normals are still pointing along the original copy direction. And after this, they're just pointing along the line. So that seems like that's what that's doing. And we can also make note that we have a few attributes it's creating that we aren't actually using to create the new normal. So these are probably ones that we're going to be using later. There's no controls, and this seems to be a fairly technical piece of the setup, so I think we're fairly safe in concluding that we don't need to promote anything from this node, so we're not going to color it green. Now we're promoting our ID attribute to primitive for some reason that we don't know yet, so we'll have to go through the rest of the setup to try to understand why. And now we've come to our first real sort of branch in the setup. Now, whenever I see a branch like this, I like to look at both sides of the branch before I start going down any individual branch. And the reason for that is I want to try to understand why we branched before I start going into detail on any one single branch. And in this case, if we look at this one, it kind of goes into something that looks fairly technical, so I'll ignore that for now. And let's look at the other side of the branch. Okay, so it looks like, if we just zoom out, it looks like what we've done is we've branched out, and then we're going to come back together again at some point. So it seems like it's pretty important to understand why we're coming back together. And in this case, we can see that we're a wrangle node, and since there's no at p equals, we're not changing the point position. So it looks like what this is doing is just stealing some attributes from this branch, and otherwise just passing through the geometry. So from this, we can conclude that this section of the setup is creating some attributes that we're going to use later. So in our minds, we might kind of say, okay, this is kind of like a section of the setup, and we can try to understand what it does as a block before we start going into detail about what each individual node does. And the cool thing about thinking about it this way is that we can see that this block of the setup does itself have some input that's off to the side here. And if we look at what those inputs are, of course, those are our collision surfaces. So without even going into detail and looking at any of these nodes, we already know that these nodes are creating attributes, and those attributes are related to our collision surfaces in some way. All right, so let's just go ahead and step through this part of the setup and try to understand how it actually works and what kinds of attributes it's creating. So it looks like we are storing the frame number as an attribute. That's interesting. Don't know why it's doing that yet. Let's just move on. Okay, well now the normals are kind of confusing, so I'm going to turn them off. It looks like we are trailing the length of the frame range. Okay, that's interesting. Don't know why. Let's just move on for now. Time shifting to the end of the frame range. Okay, so we can tell that we now have the entire frame range stored as meshes, which we might remember is kind of similar to what we were doing in our create emitter OTL with the camera point. And that makes us kind of wonder if this is doing something kind of similar to that, where we're storing the entire frame range as a mesh so that we can do some operations on the entire frame range all at once. Now we're grouping inside our collision object. And that kind of makes sense since we know that this section of nodes is related to collisions in some way. So we might be thinking, okay, so this is how we're going to decide when tentacles start to interpenetrate with our collision surface. And we can be fairly confident in that assumption once we see that we are blowing away everything that's not inside a collision surface. All right, so we have a facet node that is removing isolated points. That seems like it's just sort of like cleaning up the geometry, so that's something we can just kind of ignore and move on. And now we are getting the smallest point number along the line. All right, so that's an attribute that we created before, isn't it? We created it in this wrangle node. So we know that that is the original point number along the line. So that means that we've isolated the part of the line that's inside the geometry, and now we're getting the smallest original point number along that line. So what might that mean? Well, because we've isolated only the part of the line that is inside the collision mesh, that means that it's the first point that actually enters the collision mesh. So that's what this smallest PT along line is going to be. And it looks like we're just promoting that back down to points, because the way that we got the smallest point along the line was by promoting it from point to primitive and using the minimum promotion method to get the smallest value. So that just means that every point along the line is going to know what the smallest point along that line is. And this is a point where we have, I'm just going to zoom in on some of these lines. This is a point where it seems like we're doing some operations on an attribute, and we may want to understand on a fairly deep level what that operation is actually doing. So let's go ahead and just create an attribute visualizer for it. And in fact, I already have, but I'm just going to delete it so that we can create another one. We're going to say plus marker PT along line, and copy paste it a couple times to create the attribute visualizer. Turn off that one, and I'll turn on visualization. And we can see that before we do those attribute promotes, we just have our original point numbers that count up as we go down along the line. And afterwards, it's just the smallest value of that on each line. All right, so now we're entering a for each. So when we do a for each, we're going to look at the end of the for each to see what it's actually looping over, and it looks like it's looping over each prim ID. And remember that that is going to contain multiple lines, because if I just go to the for each and home on it, it's going to contain multiple lines because we did our trail, right? So this represents the entire frame range that is inside a collision surface for one tentacle. So let's see what we're doing in here. Now this is odd. It kind of looks like we're doing the same thing again, doesn't it? Almost. I mean, we're changing the name of the attribute, so that's a little bit different, but we're taking that same attribute, promoting it from point to primitive, using the minimum promotion method. Then we're going to detail. Okay. So we might be really confused and not really understand what these nodes actually do. So what I like to do when I hit something like this, where it seems like it's just doing the same thing again, and I'm starting to wonder, maybe this was a mistake? So if I think it might be a mistake, like maybe these nodes were just added while the author was experimenting, and then maybe the author actually needed these nodes, or maybe it's the other way around. Maybe he just forgot to delete them from here. So what I like to do is go down through the setup and find a point that is representative of the final results, but isn't too slow to calculate. And in this case, since I know that I'm making lines and eventually they're going to turn into skinned tentacles, I'll probably look for a point where, oh, hey, look, there's a skin node. So maybe I'll just go above that. It's copying some geometry. I don't like that. It's going to be slow, so I'll just go above the copy so that I can see the lines. And that'll show me kind of what the setup is doing. And since we're looking at collision surfaces, maybe I'll just control-click on the template flag to show those collision surfaces. And let's just kind of see what the difference is if we bypass those nodes. So again, we're looking at these nodes and trying to figure out what they do. We think maybe it's an accident that they're there. So let's just bypass them and see what happens. Okay, so it does change the result. So that means that they're probably not there by mistake. Maybe they're there to fix something. So we might look at the collision geometry and kind of look around and try to see how these nodes affect the final result. Since I made the setup, I happen to know what the nodes are for, so I'm going to just zoom in on a part that makes it easy to see. And we'll just scrub through the timeline. Okay. Well, that's kind of a bummer. It looks like this tentacle is intersecting with the submarine. So I wonder what happens if I unbypass the nodes. Oh, it fixes the interpenetration. And if I scrub through the entire timeline, it looks like nothing is interpenetrating with the submarine anymore. So it's impossible to say for sure, but it looks like maybe these nodes have something to do with preventing interpenetrations with the collision objects. Which kind of makes sense, because if we think about it, they're grabbing the lowest point along the line, which means it's the first point along the line. If we were to just sort of like run along the line, it's the first point along the line that actually intersects with something. And if we didn't do it from the first point, then the line might just go down and grab some other point that intersected, like down here. And then it might still be intersecting with this submarine. So that's probably what these nodes are doing. And the fact that it isolates the one containing the lowest PT num as the very next node kind of supports that theory. I'm just going to turn off the collision mesh now and home in on whichever one it's chosen. There it is. All right, so if I just turn on my attribute visualization again, we can see that these all have the same min point. So in other words, these are all of the frames of this tentacle where the first point that intersects with a collision mesh is point number 37, and that should be the lowest one because of these attribute promotes. Now we're moving on, and we see that we're doing just the same process all over again, but on the cur frame attribute. So we're promoting from point to detail, finding the smallest frame. So we can say, okay, so this is finding the first frame where it intersects and just isolating that. Then we're creating some kind of attribute, which is, instead of using the point number that we have that's all messed up because of all of our looping and our trails and all that kind of nonsense, we're just using this sort PT attribute that we created. I think it was on this attribute wrangle. No. It is here on this flow normals. We just created it as sort of like a log of, this is the original point number, and we're going to try to maintain this point order. And then we're done. We created some attributes that are somehow related to the collisions. Yay! Now let's see which ones of those we actually are transferring. Okay, so we're creating an attribute called stick frame, which is just grabbing cur frame from here. And if we remember, cur frame is going to be the first frame where it intersects. We're also grabbing that actual lowest PT by sort, and that tells us what the lowest point number along the line is that intersected with the collision objects across the entire frame range. Now, that was a fairly complicated concept to wrap our heads around, and we may have gone through all of that and still not quite understand how it works. And that's probably fine. We didn't really find anything that we wanted to promote in there. So if we didn't quite understand all of the details of this, all we need to know is this is creating attributes that are somehow related to collisions, and that's enough for us to be able to make OTLs. So we might just end up just thinking of this as just a block of nodes that does something necessary, and just kind of leave it alone. Another thing to think about is that it seems like we've kind of left the creating lines part of the setup behind, and we've started kind of going into, now we're dealing with collisions. So if we're thinking about what the steps are that will be required to build our setup, we might think, okay, so this is actually a separate OTL. So we can start planning that right away and just say, okay, well, promoting the ID to prim, that's probably something that we should consider an output of the setup. So let's just drop all of this into a network box. And we can name this create lines. And that'll just be a note to ourselves that, yes, okay, so this is a logical section of the setup, and maybe we'll be making this into its own OTL. And it doesn't seem like maybe we're done with the collision surfaces yet. There's some lines that come down from here and go down into here, so maybe we won't quite make the collision surface netbox yet. All right, so now we're branching again. So what do we do when we branch? We try to understand why we branched, and we do that by looking at both of the branches. In this case, we have an isolate stuck blast here, and an isolate not stuck blast here. And it looks like we go down and do something on this side with the tentacles that are stuck to the collision geometry. And then we merge them back with the ones that aren't stuck. So that's fairly straightforward. I'm just going to turn off visualization for now. And we can just step through this. All right, so we are promoting our stick frame to primitive. We don't really need to understand why yet, so let's just move on. We're creating an original point number attribute. So that's interesting. We have a for each loop. So let's just look at the bottom, see what it's looping over. It's looping over stick frame, which is the attribute that we created here. And that's the frame that it's actually sticking to the collision surface on. So if we just look at our delete, it looks like it's just isolating. It looks like it's just isolating the current tentacle based on whatever the for loop value is. And then it is time shifting to that value. So we can conclude that this for loop is for each set of stick frames, time shifting our tentacles to those stick frames. It seems fairly straightforward. So now we'll just move on. It looks like we are creating some attribute that represents all of the points that are highest than our lowest PT along line attribute, which is something that we also created here. So by the name of the attribute, we can say this is probably something that represents the parts of the tentacles that are stuck to the collision surface. But that's kind of dubious to make that assumption. So if we really want to be sure, we might just say something like at CD equals 0, and then just say at cd.r equals at is stuck. And that shows us that, yes, indeed, if we turn on our collision surfaces, it seems to be red for every point that follows the point that first intersected with the surface. Which isn't quite the same, you'll notice, as the points that are inside the surface. So this kind of gives us another clue as to what this block of nodes was for, since this created the attributes that we're basing this is stuck attribute on, right? So we can conclude that this block of nodes is creating attributes that allow us to generate this is stuck attribute in such a way that we know all the points that follow the point that intersects with the collision surface, instead of just the points that are inside it on the current frame. All right, so we have another for loop. So we go to the bottom, we're looping over perm-IDs, so it looks like we're just going over each tentacle individually. And by the way, I'm just going to go ahead and get rid of this visualization since we don't need it anymore. Now, something to make note of here. No. Okay, so it looks like we are looping over each perm ID, as we said. So we're going to loop over each tentacle individually. So let's see what we're doing. We have a node called travel along surface, and aha, it has a bunch of spare parameters. That means we mark it green, because we're probably going to want to be able to control how the tentacles travel across the surface. And in fact, if we set our display flag at the end of our loop, we can see that indeed we are finally having our tentacles move along the surface. Now we might go through and try to understand how all of this code works, but for the sake of time in this class, I'll just leave that to you if you want to try to figure it out. But we can generally kind of understand the way it works by just playing with these parameters a bit. So we can see wrap amount kind of makes them curl up more. And we have some standard noise parameters as well. Okay, it looks like we're just smoothing out and raying onto our collision surface to make sure that we're actually sticking to it. Another thing that's interesting is that we are storing the point intersection normal. And it looks like we are renaming it so that we can make changes to the normal without losing the original RAID normal. That'll become important later, I'm sure. We're doing some sort based on that attribute that we mentioned earlier that is just storing, if we look at our flow normals, it's just storing the original point number. So we can kind of see that we're trying to maintain our point order as much as possible, which is a good thing to do. It's a good thing to be in the habit of when we're making setups. And it looks like we're retrieving writhing. Well, it has a spare parameter, so we'll color it green. And let's see, it looks like it is using the geometry from the first input, but we are changing the point position, which means that we may be retrieving something from the second input as well. As it says writhing, let's just move the, aha, okay. So it looks like what this node is doing is just, if we look at our sort, we don't have any animation because remember we time shifted to the frame where it first intersects with the collision surface. So it looks like we're just retrieving the animated noise that we originally had. And since we're doing some kind of fit with ramps, and we have a ride the long line ramp here, it looks like we just have some control to decide how much of the animation to retrieve close to the collision surface. And in fact, we can just play with the ramp a bit to see how that works. If we, something like this, we can kind of see that it can add some animation that's quite close to the surface. All right, moving on, we're just merging everything back together. We're doing another sort to just make sure that we retained the original point order. We're just doing another sort to make sure that we retained the original point order. And now we're talking about thickness, which we can kind of say doesn't sound too much like us talking about collisions. That sounds more like a skinning type of attribute. So I think we have left behind the collisions and we're into another OTL. So let's just go ahead and move these down. And let's just grab everything that's related to collisions. We might include these, we might not. This looks like it's just a merge and it's converting it to VDB for some reason, so maybe we'll just exclude those for now. And let's just drop these into a subnet as well. Sorry, not into a subnet, into a network box, so that we can say this is dealing with collisions as a reminder to ourselves. All right, so at this point, I'm going to start moving very quickly through the rest of the setup and just kind of explaining how it works, because I think we've kind of gotten the gist of how to plan and parse these setups, and I don't want to bore you too much by repeating myself. So we're just going to kind of step through here. We have some noise. Let's mark it green. We're lifting stuck ones by thickness. We can kind of see that it's just using the ray n attribute that we stored to kind of push the lines out. We don't really need to control that, so we won't mark it green. Doing flow normals again. Up vector for stuck ones. It looks like it's only applying to the parts of the tentacles that are stuck, and it's just making it the opposite of the rayed normal, which just means that the part of the tentacle that has suckers is going to be facing inwards. Lots of spare parameters, mark it green. And since it affects only those that aren't stuck, it looks like it's just twisting up vectors. Since we're dealing with up vectors in general here, we might create an attribute visualization for up vectors, and then just play with our parameters a bit to see what these parameters do. In this case, we can see that it's how much it twists, how bendy it is along the line, and so on. Just turn that off. Here we have something that just looks like it's storing the number of points in the line, so there's no spare parameters. We probably don't need to promote it. Now we're doing a copy, and if we just step through the things that it's copying, it looks like it's just some procedural modeling stuff. That's fairly straightforward. None of these things look all that useful to promote to an OTL interface. We'll just make a mental note that we're creating a sucker surface group that represents the part of the tentacle that we're going to be copying suckers onto. And we're creating some basic UVs out of the bounding box. Down here after the copy, we're going to modify the UVs based on the line offset attribute that we created before. And this just means that each skinning surface is going to have its own UV position, which is important for how we're going to be moving the suckers. We have here our ID going to a primitive attribute so that we can then loop over that attribute. And here's where we're doing the actual skinning and cusping so that we get some nice sharp edges there. You can see that if we don't cusp, our normals are going all out of whack. Now we've got a branch. We're going to look at both sides of the branch and see if it merges together. In this case, we have the sucker surface isolated, and then we just have all of the rest of the tentacle over here without the sucker surface deleted, note. So from this, we can conclude that we are going to be using this sucker surface to generate some new geometry that we're then going to be merging together. So let's see how that works. It looks like we're branching again, and we merge back together in an attribrangle, which it looks like we're doing some manipulation of the position of whatever comes into the first input, and that's based on the second input. So that's good to know. All right, so we are going to be time shifting to the start frame, promoting our sucker surface group to primitives, and scattering based on it, which gives us a bunch of points And that looks suspiciously like points that we're going to be copying suckers to. And now once we go to the edge of angle, we can see that our UV sample is just grabbing the point position so that our points travel along with our sucker surface. Now we're doing some kind of p-scale thing, so we'll just color that green because we have spare parms and these seem like useful things to be able to control. We have our copy that does indeed copy suckers to our scattered points. So let's just look at our various sucker nodes. Some of these nodes might have parameters that are useful to promote, like our radius, for example, and various extrusion attributes. So let's just go ahead and color those green. And now it looks like we are creating colors, which are, of course, things that we're going to want to control. So let's just, as it finishes cooking, go ahead and color all of these color stops green. And now we are at the end of the system. And hopefully we have at least a basic understanding of how the system works, enough to be able to create OTLs out of it. The only thing we really have left to do is to decide what OTLs we're going to be creating out of this part of the setup. I'm just going to quickly make some decisions about that. It looks like we have a skinning part and we have some part that makes suckers. It might be cool for the part that makes suckers to be its own OTL. So how about we just drop that into a netbox. Make suckers. And then the part that does the skinning, maybe we'll drop that into a netbox. And there's some nodes at the end to merge things together and compute velocity. We might even just say, here's a bunch of nodes that are related to rendering. So we'll just make that another network box for rendering. And that is our tentacle setup, organized and ready to go for OTLs.